A very good evening to everyone. On behalf of India Space Lab, I welcome all the participants to today's session. It is my privilege to introduce our speaker for today, Mr. Shubham Sir, an engineer passionate about aerospace systems, model rocketry, and drone technologies. He completed his BTech from Delhi Technological University and has worked extensively in UAV fabrication, aerospace design, and student rocketry projects. He has mentored students in model rocket design, propulsion systems, and CFD based aerodynamics analysis. Currently, he's working with Raman Research and Innovation as a drone design engineer and is actively contributing to the development of a student payload launch vehicle mission targeting an apogee of 100 kilometers. So, we are truly honored to have you with us today. With this, I respectfully invite Mr. Shubham Sir to take the session forward.
Hello, am I audible?
Yes, sir, you're audible.
Okay. So first of all, thank you, Tanu, for the introduction, for this warm welcome, and good evening, everyone. Welcome to day one of the simulation workshop. My name is Shubham Khandelwal, and over the next 3 days, we are going to learn what is aerospace simulation, what are the numerical methods, the CFD and FEM, and all those methods that are basically used in the aerospace field or in mechanical field, civil field, either of them. Okay, so we'll be just going from the simulation sounds cool to just ran one myself, right? So before starting, first of all, pardon my presentation making skills. Okay, I'm not a very professional in that, right? Second, I know you guys are curious, right? So you'll have your questions uh, within this session, during the session, right? So make sure you ask those questions, okay, but make sure that don't interrupt the flow of this session, right? Just type your doubt in the chat box, and one of us will take those doubt and will answer that. If any answer or if any question remain unanswered, then I myself will answer those questions by the end of the session and during the mid of the session also. We'll take a break of 5 to 10 minutes and we'll answer those questions, right? So, and the second, third thing, sorry for my camera. Right now, my web camera is not working properly, but I'm fixing that, and maybe by tomorrow or day after tomorrow, it will get fixed. Okay. So, yeah, let's start with our day one. So today is all theory, and yes, I know by theory you guys must be getting like those things that theory and all, right? But don't worry, bear with me. Okay. So I'll promise that this isn't going to be like your numerical method textbook. Okay. Those were specifically designed to make people switch majors, right? So this one has aerospace stuff in it. So stuff in it. So at least what you are confused when you are confused, okay, it will be because of rockets, right? So by the end of today, you'll understand exactly what happens when a simulator crunches a mesh, the real mathematics under the hood, and day two and day three are sim scale hands-on sessions where you'll actually run FEA and CFD analysis. Right? We'll be using sim scale for this session because it's easy to use. It is browser based. Okay, you don't have to install anything. And very important thing is it's free for students. Okay, you just have to log in with your college ID and it's free for all of other softwares are also there. OpenFOAM is there. You can also do CFD in SolidWorks also. Okay, and there is one software which is very famous among all of us, that is ANSYS, right? But we'll not be jumping to those heavy uh, software, right? We'll just fix to SimScale. After you learn SimScale, SimScale is basically first step for first easiest software for this analysis and all, right? So after you are done with SimScale, you can try the same thing in ANSYS or any other software also. Okay. And in this session also, we don't want to promote like how to install a crack version of ANSYS, right? So we'll be avoiding that, right? So because of that, we'll stick to SimScale only. Okay. So think of today as the map, right? Day two and day three are actual expedition. Okay. So our agenda for today will be why simulation matters in aerospace engineering, numerical analysis, finite element method, computational fluid dynamics, the CFD part, meshing fundamentals, boundary conditions, solvers and convergence, and SimScale platform overview. Just a little bit a glimpse, okay, a sneak peek for day two and day three, right? So let's get into it. Now, why simulation? Okay, so let me just start with a question that some managers in this industry still ask, and it drives engineers absolutely crazy, right? Why don't we just test it? Okay, so the answer for a rocket is that testing it means lighting it on fire, right, and hoping it doesn't blow up your test facility. Okay, so yes, simulation is cheaper, right? So in this slide, the slide shows 100x cheaper than physical text testing. Okay, so that number isn't pulled from thin air. It's a conservative aerospace industry estimate of, okay, full scale structural testing on a launch vehicle cost millions, right? But a mesh convergence study on sim scale cost you free. Okay, right? It just costs you your free time and an internet connection. Okay. So then is 60% of your aerospace failures got first in simulation. Okay, let that sink in. Before a single bolt is tightened, software has already identified the modes, right? So that's not nice to have, right? So that's a mission. That's mission critical, basically. Okay. So that's why we go with simulation. Okay. Simulation tells you before doing the real life test. The simulation tells you that where like it is wrong or something. If it is wrong, then it will tell you, right? So you can just fix that. And the infinite test scenarios are also there, right? Think about this physically. Okay, so if you want to test a satellite bracket under 50 different vibration profiles, you'll need 50 physical test runs, right? 50 different fixture setups and 50 lab bookings. Okay, but in simulation, you loop a parameter and you study it overnight. Okay, so now let's talk from the aerospace specific context. Okay, so in rockets, the rocket nozzle experience thermal gradients, okay, of over 1,000 degrees Celsius. So, and that too within millimeter of materials. Okay, so the throat of a nozzle is the narrowest part, and it experiences sonic flow with massive heat. Okay, so and also the structural pressure. So you cannot instrument a real nozzle throat during a hot fire test and measure stress. So you basically simulate it. Okay. Then comes your satellite. Suppose a satellite in low Earth orbit, the LEO satellite, experiences a thermal cycle of roughly plus 120 degrees Celsius in sunlight to minus 150 degrees Celsius in shadow. That too in every 90 minutes. Okay. So over a 10-year mission, that's roughly 58,000 cycles, right? So fatigue simulation is the only realistic way to verify the structure, like your structure survives or not. Okay, so in this case, you can do a fatigue simulation. Okay, then in the context of aircraft, so a commercial aircraft airframes are designed for a service life of approximately 90,000 flights. Okay, or 20 years life cycle. Okay, so CFD plus FEA together build a digital life model. So that's how you get to retire the aircraft after X cycles. Okay, so these all were some little context for respect to the aerospace industry. Okay, other industries also uses this numerical methods, like in case of automotive industry. Okay, or civil engineers also do this kind of simulation, right? For structural analysis, for making a high-rise building, simulation is done. Okay, those are different simulations. In case of seismic analysis, pushover analysis is done. Okay. So yeah, those are all different other types of simulation. Mostly we'll be talking about CFD and FEM. Okay, so we'll dive in deeper into them in the upcoming slides. Okay, so we'll move one by one. Right. Now comes your third slide, that is the numerical analysis and or the foundation. Okay, so time to get a little bit mathematical, but don't worry, we'll build this up carefully. Okay, so numerical analysis is formally defined as the study of algorithms that use numerical approximation, okay, to solve mathematical problems that have no closed form solution. Okay, now what does no closed form solution means? Okay, so it means you can't write a neat formula like your quadratic formula. Okay, everyone remembers the quadratic formula, or should I like just go through it? Okay, I'll just quickly revise it to you. The quadratic formula is x is equals to minus b plus minus under root b square minus 4ac divided by 2a. Okay, I hope you all remember that equation. Okay, if not, then just Google it. Okay, that is basically the quadratic formula. Okay, it's exact, right? It's beautiful. So real engineering problems are not like that. Okay, so the equation governing stress distribution in a complex 3D solid, say an engine bracket with holes, okay, fillets and varying cross sections, right, is a partial differential equation, PDE. Okay, and PDEs over arbitrary geometries almost never have closed form solutions. Okay, so what do we do? We basically approximate, okay, but not randomly, right? We approximate systematically with mathematical rigor, okay, using numerical methods. Those methods we'll be talking about, right? Now, the core idea of uh, this numerical analysis is discretization. Okay. Now, what does this mean? Right. So don't worry, guys. I'll be providing you with the summary of the session also. Okay. Right. But you also make your own notes. Right. That is all. That would be more beneficial for you if you make your own short notes. Okay. So yeah, we were talking about the core idea of that is discretization. Okay. So the word to write down right now is the discretization. Right? Now, what does it means? It basically means converting a continuous problem into a finite number of discrete pieces. Okay, that's where the word came from, discretization. Okay, now think of a smooth curve. Okay, so mathematically, it has infinitely many points, right? But if I want to describe that curve numerically, I'll simply say it as thousand points. Okay, that's discretization, right? Now in 3D, instead of a continuous solid, I break it into thousands of small elements. Okay, triangles, hexahedra, tetrahedra, right? Each element is simple enough that I can solve the physics analytically over it, right? Then I stitch all those local solutions together. That's the entire philosophy of FEM. Okay, I know this won't be making like complete sense to you guys, but don't worry. When we'll be moving to day two and day three, you'll be seeing what a mesh is called, what a mesh looks like, and what all these discrete points looks like. Okay, so just stay with me, right? This all will make sense when we'll gradually reach to the last slide. Okay, cool. So here's an analogy for you to make life simple. Okay, imagine trying to measure the exact area under a curved roof. Okay, you can't do it with a single formula, right? If the shape is complex, obviously, there is no single equation that you can use for solving a complex shape, right? So what you can do is you can cover it with small square tiles, right? Just count the tiles and multiply by tile area. Okay. And you'll get your area of the roof. Obviously, it will be an approximation, but it will be like a calculated approximation, right? Okay. So another thing you can do is you can make more tiles, right? Because more tiles will be equal to more accuracy, right? Similarly, in this 3D mesh analysis or numerical analysis, similar thing happens, right? The more finer the mesh is, the more accurate it will give the result. Okay, so that's numerical integration, right? And it's literally what FEM does for stress analysis, right? Okay, now we'll move to the four numerical methods in engineering. Okay, the main numerical methods, right? So very first is the FEM, which we are talking from the very starting, FEM, FEA, and all that thing, right? So what is FEM? So now basically what FEM do is it divides the domain into elements with polynomial shape functions. Okay, best for it is best for structural and thermal problems, right?
Excuse me, sir.
With yes,
So your screen is not visible.
okay. Sorry guys. Wait, let me just check. I started. I hope now it's visible.
Oh, yes,
Can you
sir. It's
confirm to me?
loading. It's loading. It's not visible yet.
Okay, 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 okay. Well, let me just know if it is visible. Okay. I hope it's visible to all of you. Okay. Thank you, Shantanu. Right. So where were we? Yeah, we were at the four main numerical methods, right? So very first is your FEM. Okay. So I'll tell you again what FEM is. Okay, so FEM divides the domain into elements, which will later on will know that it is called mesh. Okay, so those complete elements make a mesh, right? So yeah, it divides the domain into elements with polynomial shape functions. Okay, so that we can calculate it easily. Okay, not we, but the software, right? Then it is best for structural and thermal problems. Okay, also for vibrational problems, right? Now, this is what SimScale uses for structural analysis, right? Then is your finite volume method. Okay, so it divides the domain, as the name suggests, it divides the domain into control volumes and enforces conservation laws, right? The mass, momentum, and energy laws, right? Over each volume. This is what virtually every industrial CFD solver uses. Okay, so some example of those solvers are OpenFOAM, right? Fluent, CFX, and again the same scale CFD solver. Okay, it is also built on this fundamental, right? Then is your finite difference method. It basically approximates derivatives using difference between values at grid points. Okay, it is conceptually the simplest, great for uniform grids, heat diffusion, wave equation, and less popular. It is very less popular for 3D geometries. Okay, so we'll be not discussing about finite difference method and boundary element method. Okay, for this session, these 3 days. Okay, we'll be most focused on the finite element method and finite volume method, right? So that brings us to the fourth slide. That is the discretization slide. Okay. Now this slide shows you our four-step pipeline. Okay, let me walk through each stage because this is the conceptual backbone of everything that follows. Right. So yeah, very first step is the real physics. Okay. So continuous PDEs, partial differential equations. Okay. Now let's discuss about those equations. Okay. So your engineering problem is described by one or more PDEs. Okay. So for structural mechanics, it's the equilibrium equation. Anyone knows the equilibrium equation? Don't worry, I'll just tell it to you. But before that, I want to know if anyone knows the equilibrium equation. I guess the chat is disabled for you, right? Then I think you can like open the chat for students
All
so
right, sir.
that I
I'm
can interact with them. Thank you.
okay. And also, I request all the participants do not spam unnecessary message in the chat.
Yes, I think we can trust on them. Okay. So, okay, after this, whenever I ask you some question, if you know the answer, just type it in the chat box. Okay. For now, I'll tell you the equilibrium equation. Okay. So it is basically V bar multiplied by sigma plus F, that is equals to your rho U. Okay. So I have also made this reference guide for you guys that I'll be sharing to you. Maybe we can see that equation in this. Let me check. Okay, so okay, that equation is not there. Okay, but don't worry. You guys can Google it, right? You are smart enough. You are engineers. So yeah. Okay, so that is your equilibrium equation where sigma is the tensor, F is the body force vector, rho is obviously your density, and U is the dynamic acceleration. Okay. Now, this PD is valid at every point in your structure, okay, continuously, right? So the problem, your structure is a complex 3D shape. Okay, so there's no way to solve this PD analytically over that geometry. Okay, so what we do after this is we discretize it. Okay, now we break it into nodes, elements, or cells, right? We replace the continuous domain with a mesh, right? And the mesh is a collection of nodes or nodes and elements. Okay. So what is node? Basically, it is a coordinate points in space, right? And elements is the connection between nodes and the connection between nodes that basically define your small regions. Okay, so that is your elements. Now each element is a simple shape. It can either be a triangle, a quad, a tetrahedron, a hexahedron, right? Anything. But the PD is transformed into a form that can be evaluated over these simple shapes using polynomial interpolation, right? Called shape functions, right? More of this is in the slide 5, right? So then we assemble and solve it, right? So the equation for that, there's this equation. Okay, this is the heart of FEM, right? After discretization, the entire problem reduces to a linear algebra problem. Okay, so here K is the global stiffness matrix. U is the vector of unknown displacements at each node, and F is the vector of applied forces. Okay, so K can be enormous, right? A real aerospace FEA model might have 5 million degrees of freedom. Okay, making K is equals to 5 million into 5 million. Okay, basically it's a matrix, right? You can see the matrix system. So the K is matrix, so it can be up to a 5 million to 5 million size of matrix, right? So solving this requires specialized algorithms. Okay, so we'll cover that in slide 10. Okay, now the post process, where you visualize your stress, velocity, temperature, and all those things. Okay. So once U is solved, we can compute derived quantities in structural FEA from displacements via the strain displacement matrix. Okay. Then stress from strain via the consecutive matrix. Okay. In CFD, velocity, pressure, Mach number, wall shear stress, and your drag coefficient, right? Now the core approximation is, we'll write this down. Okay, is U. Uh, Let me just show you the. Okay, just a second. Okay, I'll add this in the summary sheet. Okay, I'll add the core approximation. Okay, the core equation. Basically, it is ux function. Okay, that is equals to sigma 1 n1 x dot u1. Okay, this equation, right? So we are if we are solving it for ux function, okay, the complex continuous function, then we'll write it down as ux uh, equals to nx function and ui, right? So this says the real continuous field, the ux, displacement, velocity, temperature, whatever is approximated, right, as a weighted sum of shape functions n, right? So each multiplied by its nodal value ui. Okay, this is called the Gilligan approximation, right? It's how we turn a PDE problem into a matrix problem, right? So now you like instead of a algebraic equation, you now have a matrix problem, right? So this is basically what your solver solves. Okay, now okay, this slide is completed. Now we'll move to the finite element method. Now we'll deep dive into what is FEM. Okay, finite element method, right? So FEM is the basically the workhorse of structural engineering simulation. Okay, now let me walk you through the 6 steps methodically. Okay, so step one, domain discretization. Okay, you take your CAD geometry and break it down into elements. Okay, so for 3D solid structure, your suppose engine brackets, rocket nozzle walls. Okay, take example of these. We typically use tetrahedra or hexahedra, right? For thin wall structure, if any of you are from aerospace background, you must be knowing what are thin wall structures, right? Okay, so for thin wall structures, for example, satellite solar panel frames or fuselage panels, we use shell elements. Okay, and for beams and frames, suppose your truss structures, we use 1D beam elements, right? So the mesh density determines accuracy. Finer your mesh, the more finer your mesh is equals to more elements that will give you a higher accuracy. Okay, and obviously longer solve time, right? So this trade-off is what engineers spent a lot of time calibrating. Okay, now, after that, step two, shape functions. Okay, so with each element, we assume the field variable, say displacement u, varies as a polynomial. Okay, so for a simple linear triangle, 3 nodes, right, the shape functions will be n1, n2, n3. Okay, so those will be basically, okay. Okay, so write it down. I'll just uh, speak it. Okay, so your equation will be n1 is equals to, we are talking about the node 1. Okay, so n1 is equals to a1 plus b1x plus c1y divided by 2a. Okay, and similarly, your n2 and n3 equations will be there. Okay, because we have 3 nodes, right? Okay, so when we're here, the A is your element area and the coefficients A, B, C are derived from the node coordinates, right? So these shape functions have a key property. Okay, N1 is equals to 1 at node I and 0, okay, at all other nodes, right? So they form a partition unity, right? They sum to 1 everywhere in the element, right? Now, step three is your element stiffness matrix, which we discussed in the previous slide, right? So this is where the physics enters. For a structural element, the stiffness matrix is this. Okay, it is written here, right? You can see the matrix. Okay, so here the matrix B is the strain displacement matrix. It relates nodal displacement to elemental stress, element strains, sorry. Okay, so it's essentially the spatial derivatives of the shape functions, right? Then is your D matrix. Okay, it is the material constitutive matrix. Okay, so for a linear elastic isotropic material, it contains Young's modulus, that is your E, and Poisson's ratio V. Okay, and for anisotropic composites, common in aerospace, it is a full 6 by 6 matrix. Okay, so the integral is computed numerically using Gaussian quadrature. Okay, sampling the integrand at specific points inside the elements and weighing them. Okay, so for a 3D solid element with 8 nodes, hex, we typically use a 2 by 2 by 2 Gauss rule. Okay, now we'll move to the step 4, that is the global assembly. Okay, so each element has its own local stiffness matrix, right? Which we derived in the step 3. Now the global K is assembled by mapping each element's rows and columns to the global degree of freedom. Okay, those are called these global degree of freedom and the global K, right? When it is assembled, it forms your shared nodes. Okay, so this is called the direct stiffness method for a model with n nodes and 3 degree of freedom. Okay, per node, right? So K is 3n into 3n, right? 3 nodes into 3 nodes. Then very important step is your boundary conditions. Okay, so without boundary conditions, the system is singular. Okay, infinite solutions, right? So we have to give some boundary conditions to make our system solvable. Okay, so that can be either force, fixed support, or anything like that, right? So those are your boundary conditions. Okay, then we solve, right? So direct solvers, the different solvers are there. Okay, so we'll discuss about them in the day 2 or day 3, then it will make more sense. Okay, right? So till then you can look into what the different type of solvers are. Okay, direct solvers like LU decomposition, Cholsky for symmetric positive definite, right? These kind of solvers. Okay, right? So I think everything covered in the slide. Now the mathematics behind it. Obviously, we are from the very first slide, we are talking about mathematics only, right? Okay, so now we'll talk about the most mathematically dense slide of this whole session. Okay, so let's break it down piece by piece, right? So starting from the first principles, the governing equation. Okay, so the equilibrium equation for a deformable solid under quasi-static loading is V. Uh, Let me check. I should have included the equations. Okay, well, I'll give you the summary of this session. Okay, there you can look on all these equations. Right. So yeah, the equilibrium equation for a deformable solid under quasi-static loading is V into sigma plus F is equals to 0. Okay. So this is a PDE in terms of stress tensor sigma, right? So we can't solve it directly over a complex 3D geometry. So we convert it to a weak form, also called the variational form. Okay. Now deriving the weak form, like we'll derive the weak form. Okay. So multiply the governing equation by a test function V. Okay. That is your virtual displacement. Okay. Then integrate over the domain, right? And apply integration by parts. Okay. That is basically your Green's theorem in 3D, right? Okay, then is your virtual strain. Okay, the virtual will calculate the virtual strain. Okay, Just a second. Yes. Okay. Yeah. Okay. So yeah, there is this weak form. Okay, you can see it on the screen, right? This is what we derive. Okay. Cool. Now, where there is this E, okay, is your virtual strain. This strain, right? It is your virtual strain. T is the surface tension. Okay, surface traction. Sorry, the basically your boundary force. Okay, so this is the principle of virtual load, right? The basis of all FEM structural analysis, right? Now we substitute the FEM approximation, that is U is equals to matrix N, right? Where N is the matrix of shape functions and UH is the vector of nodal unknowns. Okay, so doing this for both U and V and recognizing that the equation must hold for all test functions V, we arrive at this. Okay, so this is what our final matrix will look like. Okay, so this is your governing equation, right? From this we derive the weak form, that is this. Okay, then we come at the very like easy terminal or easy equation. Okay, that is your last equation, that is this. Okay, right? So this equation must hold for all test functions, right? So obviously you don't have to go through all of those maths that we are discussing, right? That's why I haven't included the derivation. But now I think that I should have included the derivation so that it would have made more sense, right, to all of you. But yeah, this equation, that is the most important equation that you have to remember. Okay, so every term in this matrix equation has a precise physical meaning, right? Now we'll talk about the stiffness matrix, right? So assembled element, like now we'll assemble element by element, right? So K matrix is equals to that this equation that we have discussed earlier also. Okay, so here matrix B is your strain displacement matrix. Okay, for a linear element, right? And matrix B contains the spatial derivatives. Okay, the then is basically your okay. Yeah, so we have talked about the matrix B, cool. And then yeah, so matrix D is remaining. Okay, sorry. So matrix D is your material constitutive, okay, material constitutive matrix for linear elastic isotropic material in 3D. Okay, so now again there's a equation for matrix D also, but I don't think that is necessary for you guys to remember. Okay, so we'll skip that. Now in practice, SimScale reads your material properties, E, your V density, and assembles the matrix D, okay, automatically. So you don't have to do it yourself, right? So that's why we are not discussing about the equation and the formula for matrix D. Okay. Then is your displacement vector. Okay, this thing. So U, basically U, right? So U contains three transitional DOFs per node, that is UX, UY, and UZ for solid elements. Okay, and up to 6 degrees of freedoms per node, right? So basically, your displacement vector, so I'll summarize it to you again. So basically, your displacement vector is your three transitional DOFs per nodes, right? And up to 6 DOFs per node for shell and beam elements. Okay, so solving again this equation, okay, will give us the deformed shape of the structures. Okay, so for U, we compute. what we compute for u is basically your okay. So it is basically your matrix E, where is equals to sorry, the strain. Okay, so matrix strain, that is virtual strain that we discussed. Okay, that is equals to your matrix B and your displacement vector. Okay, multiplied by your displacement vector. Right. Okay, and then from stress, we compute the von Mises stress, right? Which is also analysis in the same scale thing, von Mises stress analysis. Okay, so the scalar failure criterion you'll visualize in same scale on day two will be your again strain Vm is equals to under root strain your strain 1 plus strain 2 plus strain 3 square of all, right? Then minus strain 1, strain 2, minus strain 2, strain 3, strain 3, strain 2. Okay, these all equations are in this reference sheet. Okay, so yeah, we'll look into that also. Then your third is your force vector. Okay, so force vector basically contains contributions from your applied force, right? Surface pressures and body forces. Okay, and also the thermally induced strains if coupled with a thermal analysis, right? Okay, so computational fluid dynamics, right? So I think that before moving to computational fluid dynamics, you guys must have your questions. Okay, so what we'll do is we'll just take a break of 10 minutes. Okay, so in the meantime, you can ask me any question if you have, right? Or if you want me to repeat any part, I'll repeat it for you. Okay, so take 5 minutes, hydrate yourself. Okay, we've done the hard structural math, and I hope that most of that is like understood to you. Okay, so yeah, if any of you have any question, just a second, I'll just bring my water bottle. Give me 1 minute, okay? I'll be back. Okay, so I think that we can't unmute any of you. We have only option of typing the question in the chat box. K derivation equation. Can you like little bit elaborate your question? What do you mean by K derivation equation? Like better elaboration if you can. K is the stiffness matrix. I think that is clear to all of you. Okay, so okay, I'll try that so on the whiteboard. So then it. if I pronounce it right. Basically, I'll just redo the derivation part, okay, for the K stiffness matrix. So basically, the stiffness matrix is not assumed, okay, it is derived. Uh, First, you start from the equilibrium partial differential equation, okay, that we have discussed. Okay, okay, I guess my screen is not visible.
Yes, sir.
Just a
Yes,
second.
sir.
Okay, okay. I'll just do it. Sorry, maybe internet issue. Okay, so yeah, that part doesn't require the screen. Okay, still continue. If you are listening to me, then it. Okay, so as I'm telling you that the stiffness matrix is not
Oh,
assumed. Okay,
sorry,
it is
sir.
derived. Okay, so you start from the equilibrium PD, right? That was the V dot sigma dot plus F is equals to zero, right? If you remember that equation. So you multiply it by a virtual displacement V, and then you integrate over the domain. Okay, right? Then you substitute your displacement vector, that was U, with your n matrix, right? Using your shape function, right? Then from that you get your like this derivation equation, okay, for the stiffness matrix, right? Just a second, I think that uh, wait, okay, yeah. I hope now the screen is visible, right? Okay, so yeah, this was the whole uh, part I was talking about. Okay, so this is the equation that we get, the equilibrium equation. From that we get the weaker form. Okay, this again, as I told you, you don't have to go into this all derivation. Okay, no one is going to ask you this derivation. Okay, but where it is coming from, that is that you must all know, right? So that's why the very first equation that it comes from is the equilibrium equation that we discussed. Okay, from that we get a weaker equation, okay, the weak form, right? Then from substitution and all those things, we get this governing equation, that is your uh, this stiffness matrix equation. Okay. Okay, then sir, can you explain? Okay, I'll try explaining it on the whiteboard. Because the problem is I have a mouse, right? But so drawing from a mouse will be very problematic for me. But I'll try. Which is the most countable methods in all four methods? Are you talking about these four methods, these four numerical methods, Mr. Prajwal? So if you're talking about these four methods, listen, like the every method has their own like use cases. Okay, so if you have to do a structural analysis, then you use finite element method. Okay, if you have to do the CFD part and all those things, then you do the finite volume method. Okay, and then if you have to do a thermal analysis, right, then for that there's this FDM. Okay, so each method is for different use cases. Okay, for different analysis, right? Okay, if you have to do any sound analysis part and all those things, okay, then you do the boundary element method, right? So yeah, every method is accountable, but for its appropriate use case. Okay, can computer science students contribute to FEM using programming or AI? That branch I haven't explored much, but yeah, you can. Okay, there's a lot more things you can do as a computer student or as a CSE student. Okay, you can do many of things using programming or all those things. Okay, yeah. Thank you, Pratiksha, for answering. With proper data set, you can train your AI model. PPT not visible. Okay, that problem is solved, I guess.
Yes, so now your PPT is clearly visible.
Oh, can I use Open Foam on Mac? I am not sure about using Open Foam on Mac. You have to check it. Like, don't. I'm not sure if you can use it or not. Okay, but yeah, I think SimScale is works on Mac. Okay, for Mac users, it is very tough to use these softwares like SolidWorks and ANSYS and all, because obviously you can't download the cracked version of these softwares, and the student version are very limited, right? Very restricted. Not all analysis you can do on the student license, right? So again, I'll not promote of the installing of cracked softwares. Okay, so we'll move to the next part of our slide, that is the CFD part. And okay, computational fluid dynamics. So I guess the break is over and we can start with our next part, that is the computational fluid dynamics. Before that, just a second. Theory part was always very boring for me also during my college time, but it is important. Okay, before moving into practical world, theoretical knowledge is also important, at least a little bit of that, right? So that you know what you are doing while you are doing the practical part. Okay, not just following my steps, right? So now we'll move on to the computational fluid dynamics. Okay, so now we shift from solid mechanics to fluid dynamics, right? And if FEM felt insane, CFD is where it gets crazy. Okay, so, but I'll again try to make things simple, and I'll try to use the whiteboard now. Okay, but I will not promise you that I will use the whiteboard. Okay, so the fundamental equations governing your fluid flow, okay, are the Navier-Stokes equations. Okay, so they've been around since the 1840s, I remember. Right. So we still don't have a general analytical solution for turbulent flow. In fact, proving that smooth solutions always exist for 3D Navier-Stokes. Okay. So if you if you solve it, you don't need the job. But for now, let's understand what they say. Right. So first is your continuity equation. Okay, this simply says that mass can't be created or destroyed. Right, the rate of change of density in a control volume plus the net mass flux leaving it equals zero. Okay, I hope you everyone remembers what is the continuity equation and what does it mean. Right, for incompressible flow, rho is constant. Right, so yeah, okay, so yeah, that was the continuity equation. Okay, second is your momentum equation, the conservation of momentum. Okay, Newton's second law for fluids, right? So then we have the continuity equation. Okay, just a second. I guess I have opened the wrong. Yeah, okay, here it is. Cool. So now this is your momentum equation, okay, for Newton's second law for fluids, right? So the left side is the inertial term, mass times acceleration, okay, and then your right side. is the pressure gradient force. Okay, where mu is dynamic viscosity, F is body forces, right? So the this equation governs every subsonic, transonic, and subsonic flow. Okay. Now for compressible flows, that is basically below Mach zero point 0.3, we add the energy equation as well. Okay. So then is your Reynolds number. Okay. Now the ratio of inertial to viscous forces is the Reynolds number, right? So here is the formula for Reynolds number, right? At high Reynolds number, RE, typical aerospace flows. Okay, so the flow is turbulent, right? Turbulence involves chaotic, multi-scale vertical structures. Okay, so resolving all of them directly requires mesh size proportional to RE 9 by 4. Okay, so for aerospace Reynolds number, that's trillions of cells. Okay, so computationally it is impossible. Okay, so we model turbulence instead, right? So that's what turbulence models do. K epsilon, K omega, SST, and others. Okay, so again, we'll discuss that in the slide 10, right? These models. Okay, now the CFD workflow. Again, back to the slide. So the CFD workflow, we'll discuss about what is the workflow for computational fluid dynamics. Okay, so first is your pre-processing. Basically your CAD cleanup, domain definition, right? Mesh generation. Okay, so the geometry must be watertight, no gaps, no overlapping surfaces. Okay, then your solver setup, choose turbulence model, set boundary conditions. Okay, choose numerical schemes, upwind, central difference. Okay, those things. Then set convergence criteria, right? Then basically you'll solve. Okay, you iterate. So iterative pressure velocity coupling, right? The simple algorithm, semi-implicit method. Okay, again, these are all models, okay, that I'm talking. Semi-implicit methods for pressure-linked equations, okay, and then is your post-process. Okay, so visualize your pressure contours, your velocity streamlines, Mach numbers, okay, and extract integrated quantities like your CD and lift coefficient. Okay, so that is the whole soul idea of doing the CFD. Like not only just CD and CL, but most of the time we are like calculating the drag coefficient and lift coefficient. Okay, so okay, workflow done. Now again the meshing part. Okay, the make or break step. So there's a saying in CFD that you probably should have on your wall. Okay, garbage in, garbage out. A bad mesh will give you a confident, beautifully rendered wrong answer. Okay, so once again, garbage in, garbage out. A bad mesh will give you a confident, beautifully rendered wrong answer. Okay, so meshing is where most simulation projects succeed or fail. Okay, not the solver, not the boundary condition, but the mesh, right? So the first part is your structured mesh. Okay, so elements in this elements are arranged in a regular pattern, right? Like a 3D grid of bricks. Okay, so each cell has a known neighbor. The known neighbor, right? Okay, yeah. So then is the again the advantages of using structured mesh. Okay, so basically it has lower cell count. Okay, for equivalent accuracy, better convergence, more accurate for boundary layer flows, right? Then your disadvantages, extremely hard to generate for complex 3D shapes. Okay, it requires significant manual effort, right? Which we'll discuss when we'll do the CFD part in the day three. Okay, it also includes the topology planning and all. Okay, then is your unstructured mesh, which is basically tetrahedra or triangles. Okay, so the in this the elements are placed automatically by meshing algorithms, right? That your basically the software does this for you. Okay, so the mesher handles complex geometry with no manual topology. Okay, so this is what SimScale's automation generates by default, right? So the TET meshes or the tetrahedra meshes are excellent for getting a simulation running quickly on complex CAD. Okay, but they require more elements than hex. Okay, for the same accuracy, right? By roughly a factor of 3:5. Okay, so then is your hybrid mesh, right? Mix of both world. Okay, so the industrial standard for high quality CFD is basically prism layers. Okay, so prism layers are extruded from wall surfaces to capture boundary layer physics accurately. Okay, a hex or TET core fills the far field. This is what you'd find in production grade aerospace CFD setups. Okay, right. Then we'll talk about the mesh quality metrics. Okay, so these are not arbitrary thresholds, right? They are the numbers that determine whether your simulation is mathematically valid or not. Okay, so if your skewness is less than 0.85, okay, then again, it is going to be like need some tweaks and changes. Okay, so now what is skewness? Okay, skewness, it basically measures how far a cell deviates from the ideal equilateral shape. Okay, high skewness causes large interpolation errors. Okay, so different softwares demand different these requirements. Okay, so ANSYS recommends less than 0.9. Okay, OpenForm starts complaining about 0.85. Okay, so like we'll take the average as 0.85, right? Now, then is your aspect ratio, okay, less than 5.5 is to 1. Okay, so the ratio of longest to shortest edge is your aspect ratio. Okay, so very elongated cells will lead to high aspect ratio. Okay, and it can cause numerically instability. Okay, so that's why very large aspect ratio is not also acceptable. Okay, then is your orthogonal quality, which is again should be less than 0.15, right? So it measures the angle between the face normal vector and the vector connecting cell centers. Okay, so poor orthogonality introduces interpolation error again in your gradient calculations, right? Then okay, then boundary conditions. Okay, where you define your problem, right? So a simulation without boundary conditions, as I told you, is like a system of equations, okay, with more unknowns than equations, right? So boundary conditions are how you tell the solver this is the physical scenario I am analyzing, right? So and they must be physically correct, right? Wrong boundary conditions gives you a perfectly converged, beautifully post-processed wrong answer. Okay, so you have to select your boundary conditions precisely and what you want from that analysis. On that basis, you have to select your boundary conditions, right? So now there are different boundary conditions in FEA, right? First is your fixed support. Okay, so all degree of freedoms at those nodes are set to 0, right? Suppose if there is some welded parts, okay, some bolts in your structure. So in that case, you assign that part or that face as a fixed support. Okay, so well, like, it basically simulates a perfectly rigid connection, right? Bolted joints, welded bases, right? So yeah, then is your force, right? So force or pressure. External loads, like again, these are external loads, right? In FEM, distributed pressure P on a surface is converted to equivalent nodal forces, right? So these are your force and pressure, right? Which you can assign to any face or any side, right? Okay, then is your symmetry plane. Again, if your geometry and loading are symmetric, right? So you can make a symmetry plane in your CAD thing, right? then you only need to model your half quarter, right? Or eighth. Okay. So this will basically reduce your solve time. Okay. So, or and also it will decrease your DOF count, right? By 2x or 8x. Okay. Then is your thermal load, right? So if you have run a thermal analysis first, suppose a temperature distribution. So those temperatures are imported as initial strains in your structural model. Okay. So this is thermomechanical coupling. Okay, critical for rocket nozzles, re-entry vehicles, and any high temperature aerospace structure. Okay, then is your cyclic symmetry. So it is basically for periodically repeating geometry. Okay, for example, your turbine blades, satellite dishes, right? Or satellite antenna dishes, right? To be precise. So you model one sector and apply phase shifted boundary conditions in the periodic phases, right? That basically reduces your model size by the number of sectors. Okay. Then CFD boundary conditions. Okay. Those all were your FEA boundary conditions. Then we'll talk about the CFD boundary conditions. Okay. So first boundary condition, CFD boundary condition is your velocity inlet, right? So you basically specify the inlet flow velocity, right? The direction and the intensity. Okay. So turbulence intensity I is typically 1 to 5%. Okay, for wind tunnel inflows, and up to 10 to 15% for engine nacelle inflows. Okay. Then velocity inlet done, then is your pressure outlet. So set gauge pressure is equal to your zero, right? At the far field exit. This is Newman's boundary condition, okay, on pressure. The solver calculates the actual pressure distribution internally, right? So you just have to fix the gauge pressure for the exit, okay, the outlet pressure, right? Then is your no slip wall. Okay, so at solid surfaces, fluid velocity is equals to zero. Okay, relative to the wall. This is physically correct for viscous flows, right? And generates the boundary length. Okay, so the thin region of shear flow near the surface, critical for drag and heat transfer calculations, right? Summary and periodic, same logic as FEA. Okay, it basically reduces your domain size for symmetric or periodic geometries, right? The symmetric plane and cyclic symmetry. Okay, then is your far field, right? So basically, it's for external aerodynamics. Okay, so free stream velocity and pressure at a domain boundary far from the body. Okay, so the rule of thumb is the far field should be at least 20 body lengths away from the geometry. Okay, to avoid blockage effects, right? Mm. Okay, so now comes the solvers and the convergence. Okay, where you basically trust your results, right? So now you have built the geometry, meshed it, right? Set your boundary conditions. Now you hit run on your software, whatever you are using, and what actually happens, right? And how do you know when to trust the answer, right? So that we will be discussing in this slide, right? So now again, there are some FEA solvers, right? So first of them is the direct solver, right? It basically factorize your stiffness matrix, right? And once factorized, it basically solves for different force vectors, right? So again, the I'll try to explain it as much as I can, okay? But I know that it requires some visual interaction also, right, to understand this. So again, this I shouldn't say, but for this solver and convergence part, after this session, I'll try that tomorrow. I'll make some visual interaction also for you guys to understand what is solver and convergence, right? So that you gets it more easily. Okay, right? Because right now I'll just read what direct solvers are, what iterative solvers are, right? And what are these CFD convergences, right? But again, this won't make much sense to you, right? But when I'll show it to you, then it will make complete sense. Okay, so don't worry if it goes above your head, right? Right through your head, not through your head, but above your head. Okay, so don't worry. We'll again discuss it in the next session, which is the uh, tomorrow, right? So we'll discuss it in that, right? Using some visual interactions and obviously sim scale platform also. Okay, so for now, I'll just tell you what these solvers are. Okay, so yeah, we have the direct solvers, right? And this basically factorize your K matrix, right? Okay, then is your iterative solvers, okay, PCG, GMRE, GMRES, okay. So yeah, the right. Then is your model analysis. Okay, model analysis is not used much, right, in the aerospace field. Most of the time, direct solvers are enough, and sometimes iterative solvers are also used. Okay, so then is your CFD convergence. Okay, this part. What I'll do is I'll just explain it to you in the next session only. Okay, otherwise it will be very problematic for you and me also to explain, right? So we'll just for now, for today, for the remaining session, we'll just quickly go through what is SimScale. Okay, we'll just take a sneak peek, right? A little glimpse of what SimScale will look like and how will you start or will use SimScale. Okay, for the first time, right? So okay, well, I'll just open SimScale. I think that I have already logged in it. Okay, so we have logged in SimScale. Right, so these are some again some test analysis that I did. The pushover analysis I was talking about, CFD, right? This will how CFD will look like. Okay, this is basically a domain, the square thing. Okay, you have to first define your domain for a CFD analysis. This is what FE analysis will look like. Again, this is the result of CFD analysis. Okay, so these are some test projects which I did. Okay, so this is how your sim scale will look like. Okay, so first of all, you have to log in. Try logging in with signing in with your college ID. Okay, because from college ID, I think that they give extra hours of usage. Okay, so try signing in with your college ID, right? Your organization ID. Okay, so when you log in. Okay, so from the here you'll start a new project. You will basically give the title for this project. Okay, whatever category it belongs to. Okay, let's give some title. Workshop tutorial for now. Okay, learning, learning numerical analysis, right? And then a tag CFT for now. And we're just giving a random tag. Aerospace and defense. Okay, so obviously you can't make it private because for that you'll need upgradation. Okay, subscription. So public, we'll use the public domain only. Now this is what your workbench will look like. It's taking time. Okay, so right now I don't have any CAD model, okay, because the laptop that I'm using is not my office laptop. Okay, so in my personal laptop, I don't keep these CAD files. Okay, so for now, just think of it like will be, I have uploaded a CAD model. Okay, so basically, whatever CAD model you want to analyze, you just upload it here. Okay, Then after that, in this part, right? Uh, okay, let's download one very fastly. Okay, we'll download one. Right. Grab card. I'll not do analysis right now. Okay, I'm just telling you like a bit, little bit of it. Right. So okay. For now, let's download a pipe. So complete assembly. Okay, we'll not download the assembly. You can also upload assembly also, right? But for that, you just have to upload the whole folder. Okay, not just single file. Just upload the whole folder, and it will get uploaded. Okay. Okay. Let's analyze a gear. I don't know why it requires analysis, but we'll download it. Signing in, obviously, it will leak my email ID, so I'll have to stop share. Okay, and then I'll log in. Sorry, guys. I can't just distribute my email ID. So just a minute. Did any of you already knew about GraphCAD, or is it your first time? Okay, cool. So if you are using GraphCAD, then you must be knowing about, you must have developed some CAD model also of your own. Just a second to file this. Okay, now I can share this. Yes, so we're downloading this file, right? Done, I guess. Okay, let's see if we can upload a cat part. Did any of you like have previously used any analysis software, like simulation software like these? Okay. And what softwares did you use? Mostly, I think it's ANSYS only. ANSYS, okay. Hmm. ANSYS and Symulus, right. Okay. OpenVSP is also good, but I don't find it very UI UX friendly. Okay, but yeah, OpenVSP is good. Okay, so now this is how you. I hope you are able to see my pop screen. Screen. Just a second. I'll just share my entire screen. Okay. I hope now you can see the pop-up screen, right? Okay, so here you can see the different type of simulations that we'll be discussing one by one in the upcoming session. Okay, so here it is the incompressible fluid flow, right? The multi-purpose compressible fluid flow. Obviously, we won't be able to use the compressible flow, okay, because I don't have the subscription. Okay, but most of the thing that we use in the daily life as a student, as a college student, that you must be knowing, will cover all that, right? All those things. Then your structural analysis, the static analysis, dynamic analysis, right? Heat transfer, okay, all those things. So this is basically for CFD, the incompressible and all those things, and this is for your FEM analysis, okay, right? So let's just say that we'll do the static analysis. I don't know why I like what it will look like for the students that haven't used these kind of softwares. Pardon my internet connection, right? So now this is your workbench. Okay, this is a CAD model, right? Whatever CAD model you want to analyze, right? If you have one, then it's good. If you haven't, then make one for the tomorrow session. Okay, make a CAD model, basic CAD model, whatever you want to, or just download it from GrabCAD. But if you are aware or with you have used the CAD software, then I would advise you to make one. Okay, by your own, right? So yeah, this is the CAD model that we want to analyze. Then we have selected the simulation. Okay, for now we are doing a static simulation, right? So these are again some conditions that we'll be defining, right? Contacts, connectors. We'll be discussing about them in the tomorrow session. Okay, because if I cover it today only, then not much won't be left for today, tomorrow session. Okay, so you basically define your material, okay, whatever material you are using, you'll be using. Then these are the boundary conditions that we discussed. Okay, so we'll see that as you can see, there are different boundary conditions. Okay, this is the fixed support, the fixed value point mass, right? These all are there. Yeah. Now, obviously, you won't be seeing the CFD boundary conditions because we haven't selected that simulation. Okay, we are doing the FEM simulation, right? So that's why only these boundary conditions are appear, right? Then here is your mesh that we discussed. Okay, so for now, basically the SimScale software makes the mesh itself. Okay, for you, right? You can iterate it. You can select it like you can change it according to you, the fineness and all those things. Okay, advanced settings are also there that again we'll discuss. Okay, so these again are all conditions for your mesh, right? Then you, after all these things which you define, you do the generate part of the gets generated and then this simulation run. Okay, obviously it won't run right now because we haven't defined the conditions, right? So this is here and there what we'll be discussing and what we'll be working on in the day two and day three. Okay, but again, today was just a glimpse of that, right? So back to our so not it's not a brand endorsement, right? So it's just basically some information about what software we'll be using, right? So that was it, right? And then again, it's a workshop, a roadmap. It should be in the starting, but yeah, in the day one, this part is remaining, right? Else we have covered. If you want, I will give you this summary student reference guide. Okay, you can go through this, and then again you can read it one, two or three times. Okay, then it will be clear to you, right? What we discussed today. Okay, then day two will import a rocket fin. Okay, or any other aerospace airplane component. Okay, We'll assign its material, again same workflow. Okay, we'll visualize the von Mises stress analysis, right, and the displacement analysis. Okay, then on the day three, we'll be doing the CFD analysis, right? We'll import a nose cone or fairing geometry, right? We'll build a wind tunnel domain around it that I showed you in this thing, right? This is your domain, but obviously we're making a very like more accurate and precise domain. Okay. Then we'll set our velocity inlet, we'll apply a turbulence model. Okay. And there was one question also in the chat box. Someone was asking that, sir, we can, why is turbulence modeling considered difficult in CFD simulations? That you'll see on the day three. Okay, Viraj, like telling you right now will be very difficult, okay, for understanding. You'll see it in day three. Okay, that why turbulence modeling is considered difficult, right? Okay, so mm, okay, yeah, everything covered. Okay, so let's lock in today's five key ideas right before winding up the session. So first is the numerical analysis that converts real physics into solvable matrix systems. Okay, so the real world is governed by PDs as we discussed. Okay, so we can't solve them analytically over complex geometries, right? So what we do is we discretize them, right? We discrete them. Okay, then again, we define some shape functions. Okay, then we do the method transform, right? The PD into those that equation, the K matrix displacement is equals to force matrix, right? That equation or its equivalent in CFD. Okay, so yeah, mathematics is the bridge, right, between physics and computation. Okay, so mathematics is important, right? Then is your FEM, solve structural problems by discretizing geometry into elements. Okay, so the stiffness matrix encodes both geometry and material. Okay, via the B matrix and the D matrix, right? So solving the equation that stiffness matrix equation, right, gives you nodal displacements. Okay, so from which we derive strain and stress everywhere, right? So von Mises stress is the scalar failure criterion we'll use on day two. Okay, which we discussed, right? So then is your CFD solves fluid flow using Navier-Stokes on a computational mesh, right? So the non-linear convective term makes CFD iterative. Okay, so the simple and those piezo algorithms, right? That basically decouple your pressure and velocity. Okay, how that again, practically it is more better for you. Okay, to understand, right? Then your meshing quality, right? Obviously, we have discussed that meshing quality directly determines your accuracy and convergence. Okay, so those factors, those skewness, aspect ratio, the orthogonal quality. Okay, so yeah, they are mathematical constraints. Okay, on the accuracy of the numerical scheme. Okay, so that was your fourth point. Then as your fifth point, again, SimScale, not SimScale, but any other software. Okay, brings all of this to your computer. Okay, but SimScale, what SimScale do is it basically uh, makes brings it to your browser. Okay, so no setup is needed, no heavy RAM or storage things are needed. Well, obviously, a little bit basic uh, things are needed, right? So your laptop has a minimum of 8 GB RAM and more than that. Okay, or a basic graphic card. Okay, a basic graphic card is required, not a very high graphic card. And integrated graphic card is also good, right? So now then again, Codester is there. Okay, if you want to use that software, Codester is there for FEA. Okay, OpenFOAM is a very good software if you want to use for CFD. Okay, then OpenFOAM is also there because they have launched a not a new thing, but I think that was previously there, that you can use composite materials also for your analysis in open form. Okay, and now most of the time in this aerospace industry, most of the time composite materials are only used. Okay, mostly in these drones and rockets and satellites, right? So for a better analysis, for a better result, you must also define your material accordingly. Okay, so open form is good for that, right? And then again, there are more different softwares as we have discussed that ANSYS is there. Okay, you can also even use SolidWorks, right, for these kind of analysis. But I won't recommend using SolidWorks because again, it is not that accurate. Okay, so using a dedicated software for these kind of things is much preferred, right? So okay, so yeah, that brings us to the end of this session. Okay, now if you guys have any question, okay, regarding the session, you can ask in the chat box, I guess. Please, sir, give a short recap in Hindi also. Okay, Hindi. I don't know if that's possible, Viraj. Okay, but yeah, I'll send you this PPT and the reference guide. Okay, so that you can go through all of those reference materials. Okay, and like you can understand it in your own language, or you can use any uh, LLM model, right, to summarize all of this. And most of the time, you guys use that, right? Even I use that for summarizing big research papers and all those things. Okay, so yeah, you can type your questions in your chat box. Any questions if you have.
All the participants who have doubt can raise your hands, and one by one your turn will come.
Okay, or you can do this answer.
So we have a question from Shantanu. Shantanu, please ask your question.
Sir, I have some doubt in ANSYS software. Sir, can I share the screen, the whole thing in the this meeting?
Mm,
If you allow, sir, please.
I guess Shantanu, it will take some time. You, what you can do is you can contact me personally. Okay. Again, because we don't want to take
Sir,
other students' time, right?
sir, actually, I had made a CAD model there and some analysis I have done. So regarding that, I had to consult
Okay,
here.
okay. I think that okay. Go ahead, go ahead. Share your screen.
Yes, so we can take his doubt since I don't think so any
Okay,
other student has any other doubt.
okay then. If not, then we can definitely take it.
Sir, is the screen visible?
Yes, Shantanu, it's Susan. So is it the student version or the cracked version only?
Sir, is it a student version, sir?
Okay. Okay, so meanwhile, if any other student have any other doubt, okay, they can ask in the chat box. Okay, so sir, I'm using Ubuntu. Is there any free compatible tools as for now for my OS? Yes, absolutely. Ubuntu is actually the best OS for simulation tools. Okay, so you can use SimScale, right? For day 2 and 3, you can use SimScale. It's just a browser thing. Okay, and it works complete perfectly fine on Chrome or Firefox. Okay, or you can use for CFD, you can also use OpenFOAM, right? Or ParaView. Okay, and for FEA, I think there is FreeCAD. Right? You can use FreeCAD with the FEM workbench for that. Right, and for CAD, there is OnShape. You can use OnShape also. It is again browser based, right, and works on OS. For Mac, I think for Mac, you can use Autodesk, right? 360 is good. And again, SimScale is there, OnShape is there for CAD. Okay. And for CFD, again, you can use OpenFOAM on Mac. I think you can use OpenFOAM on Mac. I'm not sure. You have to check that. Right. But SimScale OnShape works fine on Mac. Right. Or you can download 360 also. I'll share the PPT with the organizer. Okay. They'll share it with you. Yeah, Fusion is good, Abhishek, for CAD modeling and all. Fusion is good. Okay, you can also do some these kind of analysis also to a limit on Fusion. So meanwhile, you can give me a little bit context, Shantanu, that what kind of analysis you did and what
Sir, it
basically.
is basically, sir, steady state thermal analysis I've done regarding, I have selected a material, aluminum or stainless steel. I've selected a material, and after that, I had just a sample. I have made a thermal analysis on that, that what sort of temperature changes will be there in that, and other such things will be there. So that
Oh,
kind of thing is there. But few things are there. I mean, I had some doubts, so I want to clarify that.
okay. Okay. Mm.
I know, sir. Sorry for the inconveniences. It is taking
No, no,
time.
no, no. I'm used to it. No issues. I think the students are not, but yeah, I'm used to it. No problem. That's the actual drawback of using ANSYS.
Sir, this is the thing I had done here. So it is basically a CAD model. So
Oh,
there is a
okay.
temperature change there. So, sir, what extra things I can add on in this, sir? Means what extra things I can do in this sample, means in this CAD model, apart from this steady state thermal analysis in the
What?
thermal domain?
Uh, I mean, in what well, like in what context or in what reference you want to do extra things? Like in same this thermal analysis only.
Yes, sir, in thermal analysis context too.
Okay. So I think I'll just like immediate steps you can take is structural coupling. Okay. Right. So what you can do is you can link this your thermal result directly into a static structural analysis. Right.
Static
So
structure.
yeah. So what will happen is your temperature field will become a load. Okay. And aluminum expands non-uniformly. Right. And that will create a thermal stress. Okay. So you can do that part. Right. I think in ANSYS you can just right click your steady state thermal and you can transfer data to new. Okay. Your static structural. Right. Or you have to look into it. Okay. By your own. Obviously, if any problems occur, then I am here. Right. Second thing you can do is what you can do is you can do a heat flux and temperature gradient plots. Okay, right. So like you have only looked at the temperature contours, right? You should also plot the heat flux vectors, right? That shows the direction and magnitude of heat flow. I don't know if the student version allows you to do that or not. You have to explore it on your own again. Okay. Second thing, the temperature gradient. Okay, where the steepest thermal gradients are, right? That's where your thermal stress will be highest. Okay, and you'll know that by the plot. Okay. Second thing I think you can do is you can change your boundary conditions, right? And you can compare your different results. Okay, or you can try with different aluminum alloys. I think you have used 6061 or any other alloy. What alloy you have used?
Yes, sir, I'm looking at that, sir.
No worries. So,
Sir, this structural steel I have chosen.
okay, okay, no worries. So what you can do is you can try different aluminum alloys. Okay, either you can do a like comparison between 6061, right? Aluminum 6061 versus aluminum 7075, because these are two types of aluminum alloy that are majorly used across the aerospace field, right? So you can do a comparison on these two aluminum alloys or any alloys you want to, right? You can like check different thermal conductivity, the K values, right? See how temperature distribution changes. Okay.
Okay.
Or I think, yeah, that three things you do first. Then again, there are different things like you can do a mesh convergence study, right? But again, these three things that you should do immediately, I think. Okay. At least you should do
So
the heat
steady
flux
is
and temperature gradient flux. Or
okay.
yes,
Sir, the structural thermal analysis, that thing, sir, and that heat flux, these things, no?
yeah, these two things I think you can try it, right? And again, if you are like doing this for a project or anything like that, right? Then you can try the about like changing the boundary conditions also. Okay, you can compare and make
Sir,
a
basically I am one means I am presently I am a pre-final year student. So after few months I will be so I am basically making a some kind of a rocket model. So
okay
for that I am trying
doing
to
this.
means
Okay,
learn all these things, basics things. So
okay,
it will
okay,
help
okay.
me in that.
Then you think then I will suggest you that you do the third thing also, right? So that you get the knowledge of different materials and different conditions. Okay, what are the different thermal conductivity values, right? You'll get to know all of these, right? So do the third thing also, but after these two things, right?
Okay, sir.
First is your
Sir,
yeah, yeah, yeah.
sir, one more thing I wanted to ask you. Sir, apart from these things, let's say, sir, if I want to draw rocket parts or some like kind of engine, like cryogenic engine parts, I am just saying, sir. So I know that in student version, no such means the advanced things will be there. So, sir, for time being now, what things I can learn from here, basically, like it is given here
Okay.
in the analysis systems or from this. component systems or whatever means whatever it is given here. So presently, what I can learn.
Okay, so you want to like explore all different things that you can do in a student license, right? That
Yes,
is
sir.
your
Yes, sir. That
question.
whole rocketry and the whole satellite and the rocketry. That thing.
Yeah, obviously in context with rocketry and all things, right?
Yeah,
So,
space. Yeah.
yeah, so Shantanu, I'll tell you one thing that I'm not very much sure that what things you can use in the student version, right? The things I'm aware of is that you can do the static structural part, right? You can do the model analysis, right? You can do a buckling analysis, right? For a thin structure, right? In with respect to a rocket, you can do the buckling analysis. You can do the fatigue analysis, right? These all are for structural thing. Okay. Then for thermal, you have already done the steady state thermal. You can do that. Then you can do the coupled thermal structural, which way I have told you that you should do. Okay. Then for CFD, you can do internal flow, right? The pipe flow, duct flow, and the valves through flow. Okay. Then again, the external aerodynamics, that is also very important with respect to a aircraft or a rocket. Okay. Then I think you can do the heat transfer in fluids also. Okay, so these all things are which I'm aware of. Obviously, there must be some other things also that you have to check. I'm not sure. Okay, what other things are, but these all things are that I know that you can do. Okay, on ANSYS student license.
No, no. Sir, can you share me your official mail ID or your number for further consultation?
Official mail ID. Okay, I think I can share your mail ID. Is it okay, Tanu, that if I share my email ID?
Sir, I'm not very sure about it, but I think it should be kept confidential.
That's why. Sorry. You can connect me with you can connect me on LinkedIn. Okay. Then to
Yeah,
only
so LinkedIn is
LinkedIn is good. You can search me with my name. I'll just share my LinkedIn profile,
Sir, I'm
or I'll
stopping the screen sharing.
it's okay. What I'll do is I'll just share it with the presentation. Okay, that I have to give to you. Okay, the PPT and the reference material. Okay, I'll share it with you my LinkedIn and all those things, all those three things. Okay, kindly not spam in my DM. Okay, okay, guys, only relevant questions. Okay, cool. Works with everyone, right?
okay. Is there any other participant who has any other doubt? Kindly raise your hand if you have doubts. So I think no other participant has any other doubt. Do you have anything to say, or shall I conclude the session?
No, it was a great session, guys. I hope my, like some things were not like completely understandable. Okay, but don't worry. I know what the things that I like not covered in this session, and I try to cover it in the upcoming session. Okay, time was a constraint for me for this session, but tomorrow is Sunday. Okay, so I have time, and I'll make a very interactive and presentable presentation for you guys. Okay, I'll try. Right. So yeah, that's all. You can take over the.
All
Sir,
right.
can you
So,
share me your LinkedIn profile or whatever it is there, sir, in the chat box?
Okay, I'll do that.
Shantanu, his LinkedIn
I'll do
ID will be shared with you. Don't worry. We'll send along the
Okay,
PPT and
okay,
the study material.
okay, okay. Thank you, sir.
that.
Thank you.
Thank you, Shanti.
Yeah. So, shall I conclude now?
Yes, Tanu, you could continue.
Thank you, sir, for such an insightful session. Thank you, all the participants. Now, you all can leave the meeting.